So we had many questions about IPv4 versus IPv6, and of course this is quite justified because it's a tricky problem. We will discuss in several modules the different tools that are used to make the two work together. Right now let's look at IP addresses, IPv6 addresses. Those are examples of IPv6 addresses like this one that you can see on the EPFL network. The routing table looks a bit different. The principles are the same, but the main difference is that in IPv6 we use link local address more frequently than in IPv4. The link local addresses are things like the red circled address. Here I'm showing the routing table of the router ED0 minus SWI, and it shows that for this prefix, so the top prefix means specific local area network, this one. The next hop is FE80, etc., 1%1. This is the IP address of the next hop, like in IPv4 was done, except now in IPv6 we use the link local addresses. Now if you're a router, you have several links, several local area networks to which you're interconnected. So you may see the same address on different subnetworks connected to you, but those are different machines because the link local address by definition have a meaning also only inside the link. Inside the link means inside the local area network. So you need, in addition to understand which address you're talking of, to put the interface number, which in this case is put in %1. In other machines you could see ETH0, ETH1, etc. So the %1 is not part of the address, just saying the interface to which this address is meant to be interpreted. We'll explain now how the IPv6 addresses are written practically. 128 bits is long. Of course, we don't write it in binary. We don't write it today in a dotted decimal notation because people find it more convenient to match from binary to hexadecimal. So we use hexadecimal now. Hexadecimal has become popular. People are not afraid to use it. So here is, for example, two addresses. There is some meaning. Now the meaning of the address is impossible to guess just by looking at the address. I know the meaning because I know that EPFL's prefix considers only those 48 bits that are written in red. Then the pink thing is 16 bits that identified which subnetwork inside EPFL, and the green part is the host part. As we will discuss a bit later, we need the net mask to understand which part is the green part. And to know which one is the pink, which one is the red, it's impossible just by looking at the addresses. You need out-of-band information to know this. So you need to go to the registry of all IP addresses to discover which prefix was allocated to which organization. Routers don't care about those things. They will just look at more local information. We also have at the second line a private address. Similar to IPv4, there are also private addresses in IPv6. The main difference now is that there are as many private addresses as there are globally unique, so public IP addresses in IPv6 than in IPv4, because there's many bits in IPv6, so we can do whatever we want. In particular, you see here that the green part is the same for the public and for the private address. So if an address is private, like happens typically in a company, many companies use private addresses, the 10 dot something, like the EPFL public LAN, wireless LAN uses. And of course, Nestlé uses the same 10 as UBS. Or let's say UBS and Credit Suisse might use the same 10 dot something addresses. Now, in companies, it happens very frequently that companies merge, split, a branch of UBS is sold to Credit Suisse, then they merge, and then they have the same IP addresses. So they need to renumber everything. So renumbering is the thing that happens when you merge two privately separate private networks that for organizational reason become no longer separate. With IPv6, we think we can avoid the problem by having prefixes that are given to companies. So this prefix is given to the EPFL Smart Grid project. In fact, there are several IP private prefixes to EPFL. One of them is this one, and it's just for the people who work in the smart grid. So it's very nice. You can use your own private addresses, but you can use for a machine that has both a public and a private one, you can use the same host part, for example, and thus make migration very easy. Now the IP addresses, the IPv6 addresses are too long, so most of the time we'd like to compress them for human notation, human readable notation. The rules are the following. IPv6 addresses are written by blocks called pieces of 16 bits. 16 bits means 4 hexadecimal digits. Between the pieces we use columns as a separator. So here is, for example, an address 200200, etc. And then if there are many zeros, we can drop them. So any zero that is a leading zero inside a piece can be omitted. This is not visible in this address, but was visible here, for example. The 620 is in fact 0620, so there is a hidden zero. Inside a piece of 4 hexadecimal digits, we omit the leading zeros. And if there are many blocks that are entirely made of zeros, we can forget them by writing nothing, with a convention that you can do it only once. Otherwise it would be ambiguous. You would not know how many zeros were forgotten. For example, this address circled in red can be more simply written as the compressed form on the right here. What I've done, I've removed all the zeros and replaced them by empty space between columns. I can, of course, this is for displaying addresses. When the computer acts or the router plays with addresses, it uses the full form, right? And this is not ambiguous because this IPv6 address has a fixed format, 128 bits, so we know exactly how many bits are missing in this part. And if there are leading zeros that have been omitted, like here, the 620 is a 0620. So those two rules, blocks of 4 hexadecimal digits called pieces, and you can remove all the zeros at most once in an address, allow to do more human readable addresses. In particular, when we describe prefixes, it's easier to use this convention. Here are a few examples of IPv6 global unicast. Unicast means the normal IP address as opposed to multicast, and global means public. We've seen that this block of addresses is allocated to EPFL. This block is allocated to Switch. Switch is the provider of all universities, including EPFL. We see a difference between IPv4 and IPv6 here. If you remember the addresses of Switch, for example, they have nothing to do with the EPFL addresses. So whereas here, the EPFL block is a sub-block of the Switch block. Right. Well, why is that important? If you are a router in the US, you see an IP packet with IPv4 destination address EPFL, and another one with IPv4 destination address ETHZ. Those two prefixes have nothing in common. So you cannot aggregate the two together. In fact, everything that goes to Swiss universities in IPv4, they have nothing in common. So you need one entry in your routing table for each Swiss university. One for EPFL, one for ETH, one for Uni Geneva, etc. With IPv6, you don't, because all universities are served by the same provider, Switch, that has 2001-620. And all IPv6 addresses of all universities in Switzerland start with this block. So this American router needs only one line, because all traffic from America to Switzerland follows the same path. So we don't need to have separate entries. This is called aggregation. So one key benefit of IPv6 is the ability to aggregate the routing tables, therefore making them smaller. Yes?
The American router needs one link to Switzerland or only to Swiss universities?
One entry to a Swiss provider called Switch.
Can the same thing be applied to 4 countries? Two countries can be assigned some
No. So the question is whether there is a block of IPv6 address allocated to a country. The answer is no, because there's no concept of country in IP addresses. There's the concept of providers, of organization to give the service. Again, remember I said an IP address is topological, but in the sense of the topology of the organizations in the world. So you might have an IBM address, a Switch address, a Swisscom address. Now Swisscom happens to be matched to Switzerland, but who knows, in 20 years from now, perhaps Swisscom will be just a branch of a pan-European operator, and then it's not specifically Swiss. So there's no allocation specifically to a country for routing, at least. Yes?
Could you have an organization like Switch, for example, like for IPv4, and then once an American router will send a message to Swiss University, it follows only one route without taking different paths?
So the observation is, why is that possible with IPv6 and why not with IPv4? We could do the same for IPv4. We could renumber all the addresses, give a block to all the switch customers, and say, you switch customer, you have, I don't know, 128 /8, for example. But the problem is, it would be possible, but it would mean renumbering. Nobody likes to do the renumbering, right? If you need to renumber the IP addresses, first, it's a nightmare. Second, the things won't work during you need a transition day from the old to the new address, everything. So we try to stay away from renumbering globally. Plus, it's hard to do because there's not many available addresses. In IPv6, there are as many addresses as you want. People have computed, I'm not sure if it's true, but the folklore says there are as many addressable entities with IPv6 as there are atoms in the universe. So 122 to the power 128 is not 4 times larger than IPv4 space, it is the space to the power 4. So we have, for IPv6, we have as many addresses as we want, so we can structure them. When we structure addresses, we waste a lot of the address space. But with IPv6, it's possible. With IPv4, it's very difficult, and nobody wants to do it today. So other addresses, as you see, Swisscom has nothing to do with EPFL, because it's a completely independent provider. You have addresses that were given in the past that are so-called provider independent, that are based on geography. So perhaps apparent contradiction to what I said before. Address allocation can be based on geography. We can give a block of addresses to a country or a continent. But that doesn't mean that the sub-blocks inside these blocks are routed together. Right? You could still be the IBM company and have a Swiss address for some of your machines, for example. Then there are more fancy addresses. Those are the ones we use in the Internet Engineering Workshop IPv6 wireless service that we give to you. And those are so-called 624 addresses that are used for solving the transition problem for IPv6 to IPv4. We'll discuss about them later. There are also special addresses like in IPv4. Nothing is typically 0 in an address field means absence of address. The same is true for IPv4. Of course, you never see that in a packet. If you receive a packet with destination address 0, it means it's an invalid address. But you put that in software when you need an address. For example, if for whatever reason a piece of C code creates a data structure and needs to it's a good idea whenever you create a data structure to initialize it to something. So you initialize it to 0 if it's an IPv6 address. And all the software will know that when the address is 0, there is no address. It's not a valid address. The loopback address is 1. So this notation, double column 1, means 0, as many zeros as you want, until the last hexadecimal digit, which is 1. Then there are also private addresses that all start with FC00/7. That means you take the first 7 bits of the hexadecimal representation FC, and anything that has the same 7 bits is a private address. And if you do this hexa to binary representation, you will find that it means anything that starts with FC or FD, because FC or FD have the same 7 bits. Then anything that starts with that and has anything after one is a private address, like the one we've discussed before. There are also the linked local address, which are special cases of private addresses, but that are non-routable, just like for IPv4. They start with FA/FE80/10. There are similarly multicast addresses that starts with FF, not surprisingly. And those are special examples of multicast. For example, if you want to send to all systems inside your local area networks, with IPv4 you send to the address made of all ones. In IPv6 we're a bit more subtle. We make a difference between all systems and, for example, all routers. Sometimes you may want to send a packet to all the routers that are in your system. For example, to discover whether there is a router connected to your LAN. Then you can send a broadcast, and you don't know the IP address of your router. With IPv4, you send a broadcast to everyone. With IPv6, you send a broadcast to all routers. Those are little, minuscule optimization that make things more complex. The IPv6 packet format is very similar, except now it's bigger, because the address is bigger. The main part of an IP header is the addresses. Now, the addresses are, of course, much larger. Each of them is 128 bits, which is 16 bytes. So there are 32 bytes of addresses, and the rest is practically the same as in IPv4. In particular, there is a protocol type, which is now called next header. Next header is just the annoying thing with IPv6 and IPv4 is the terminology has changed. It's always the same thing. The terminology of IPv4 is often misleading. For example, the time to leave is not a time, or the protocol type is not always a protocol. So in IPv6, it has been fixed. For example, the time to leave is called the hop limit, and the next header is, the protocol type is next header. But for us, practically, next header means whether it's TCP or UDP. But as we will see, when we start doing more fancy things, sometimes you can put an IP packet inside an IP packet. For example, you might want to put an IPv6 packet inside an IPv4 packet, because you have only IPv4 connectivity in your end. In that case, the next header will not be a transport protocol, but will be truly a network layer protocol. That's why it's called next header and not protocol type. The rest we will see in detail. We'll discuss again the hop limit a bit later. Does this work? So in principle, I should see some control panel that I don't see, but it should work. Now, does it work? Are you able to click?
We don't have the session number.
It's not on the internet. I've disabled the internet in a desperate attempt to stabilize my operating system.
It's not polling, I guess.
It's not polling. Okay, so the polling doesn't work. Well, we'll do it manually. 2 answers. If it would be a clicker test, if you pick the correct one, you have +1. If you click the wrong one, you have -1. And you can say, I don't know. It's tough here, there's only 2. In clicker test, there's always more than 2. Assume I would fantasize and write IPv4 address the IPv6 way, which sometimes we will do. Because sometimes you need to write an IPv4 address inside an IPv6 address. The IPv6 address is very large, so there's space to put an IPv4 address inside it. That's a mechanism that's used for the interworking. If I do this here, this address, who says it is number 1? Raise your hand. Thank you. Who says it is number 2? Vacuum. Okay, so the correct answer is, of course, number 1. That was an easy call. Of course, number 2 is not correct, right? Because this number is above 255, so this cannot be an IP address, right? So this notation, 2001 Bad Babe, is it a string of 32 bits, 44 bits, etc.? It works? Okay, wonderful. So you can click. Why don't I see? So 5 more seconds, and I close the poll. Okay, Dirac almost on the correct answer. Of course, it's 128 bits. It is always 128 bits, no matter how many hexadecimal characters are written. That's the convention, right? Which means there's lots of zeros here to make it 128 bits. Okay, that's all we will see about IPv6 so far. And with that, you're equipped to type all those wonderful IPv6 addresses in the labs. Some important thing that we've discovered last week is the subnet mask. So recall that we do longest prefix match. An IP system needs to know which addresses are in the same LAN as itself. For example, if I am the router that's here in the middle of the EPFL network, if I have a packet that goes to 15.7, 15.7 is this machine, right? The destination and myself, the router, we are on the same local area network. The IP principle says if you have a packet to send to a destination that's on the same local area network as you, you should send directly to this guy. But if I have a packet to send to that other guy, 156.24, which is a Sun machine in our lab, then you go to the routing table and you find where to send it. But to do this, we need to know, how do I know that the destination is on the same local area network as me? This is what subnet mask is all about. First, let's observe this thing that is not entirely obvious, is that in IP, one subnet, which is equal to one LAN, and this is enforced by requiring that all hosts in the same local area network must have, all IP addresses of interfaces that are in the same local area network must have the same network part. So the network part is this variable part that identifies what is the LAN. For example, 128, 178, 151. That's the network part at EPFL. All hosts that are on the same local area network must have those same 24 bits at the beginning. With IPv6, it's a bit more complicated, but at EPFL, 1, 2, 3, 4, this is the network part. The size of the network part is not hard-coded. It varies. It can be anything in theory. For example, at EPFL for IPv4 it's 124 bits, like many networks do. At ETHZ, it's more sophisticated. It's 26 bits. So there you need to start playing with decimal to binary to understand the prefix part. Very often with IPv6, people take 64 bits, but very often, not always. Okay, this was... In order to know what is the prefix, the network part of an IP address, you need to have a second information, an out-of-band information, that is called the network mask. If you don't have the network mask, you cannot be sure what is the network part. So hosts are configured not just with their IP address, but also with their network mask. And due to, I would say, computer engineering folklore, it is written in this form. The network mask is in the same format as an address. You put ones in the positions of the bits that are part of the network portion, the network part, and zeros for the host part. For example, if you do that for EPFL IPv4, you put ones everywhere in the first 24 bits and 0 after, and you write this in the classical notation for this type of address, which is here dotted decimal, and you will find 255, 255, 255.0. That's the network mask at EPFL. It's a very complicated way to say 24. Right. Why is it done that way? Because in principle, you could, with this thing, have a network mask that's not necessarily the prefix, but could be any part of the IP address. So you could have, with this theory, a network mask that is bytes 1, 2, and 4. Nobody does that ever. I've never seen any network doing that, but you can. You can do it if the software for giving masks allows it. You could in theory, and then if you have an arbitrary network mask, in order to test whether two addresses are in the same local area network, i.e. whether they have the same network portion and the same network part, you compute the network mask by applying a bitwise AND if you use this convention. Bitwise AND means 1 and 1 is 1, 1 and 0 is 0. And anything and 0 is 0. So if you put the ones everywhere, you will get that those two addresses, when you apply the mask, you obtain this. They have the same result of applying the mask. Therefore, if the addresses are correctly given, they are on the same local area network. IPv6 mask is most of the time 64 bits, which means all those many Fs. And sometimes people use the notation /24, which is used typically for prefixes inside routing tables. The network mask is a special case of it. The network mask is typically used at hosts only. For example, on my machine at some point in time, it used for IPv6 this convention. Instead of giving this lengthy sequence of F, it asks me what is the subnet prefix length. But not all machines give the same. Sometimes the smart things will ask you a length for IPv6. The non-smart thing will insist that you type in a mask with Fs. Remember, with IPv4, as with IPv6, 0 and 1 are reserved. All 1 somewhere means broadcast. All 0 somewhere mean non-existent address. Now, of course, because the address prefix might vary, you don't know whether, if you take 128.178.156.0, is it a valid address? Is it the non-existent address, or is it an address that corresponds to the 156.0? Right? So this convention makes sense only if you know the network mask. So it's not fully non-ambiguous. So in principle, you avoid the all 0 and all 1 as part of the for host part with IPv4. There is also some folklore with IPv4, which is totally irrelevant today. But many places, if you look on the internet, blogs or even lectures on masks and things, they will serve you all that stuff. In the past, there was a stricter classification of IP addresses which was mask-free. So we could work without mask by just having self-contained addresses that would be of so-called different classes. If an address has a first bit that is, for example, like for EPFL is this one. If the first 2 bits of the address are 1, 0, that means if the address is somewhere between 128 and 190 something, it's written here, 191, like the EPFL address. The network ID was supposed to be the first 16 bits. And many systems treated the network ID as equal to the network part. At that time, there was a concept of 2 levels of hierarchy. There would be a network ID, EPFL, a sub-network ID, the LAN at EPFL in which you are, and a host part. Again, this is completely obsolete today. The thing has become much more complex. Right now, there is not a there is only seen from a host. There is the host part and the network part. And then inside routers, there are variable length prefixes depending on how you do the aggregation and the longest prefix match. But this folklore continues. Those things had so-called classes A, B, C, etc. I will skip this one because I don't have enough time. I will just poll you on this one, if the polling works. At ETHZ, I said that the network part is 26 bits. What is the network mask? I close in 5 seconds. The majority is right, which is not always the case. Like, remember previous votations in Switzerland. So this is the correct network mask. Why? Well, we'll see in a second. Let me ask you for IPv6. Guess. Give your best guess. I close in 5 seconds. And the majority is number 7, which is correct. So first for IPv4, right? If we painfully write all the subnet mask of 26, that's what we get. Now we group this by blocks of 8 bits. This first block is 255, etc. So 255, 255 is the last one. Well, you need to convert, so take your calculator. 128 plus 64 gives 192. So that is the subnet mask. Of course, with IPv6, it's much less trivial. Usually it's 64, and most systems will ask you just a number. We skip this one, I'm sorry. Because we move on to the next topic. Right. So we have seen much of the addressing, not all. We'll talk a bit more next week on how addresses are automatically allocated, DHCP and the stuff. But before that, let's do our first instance of architecture violation. What I call architecture, and what many people, but not all, call architecture, in the context of networking, architecture is the law of the internet, which is in the books called the RFCs, request for comment. That's an obsolete name. There is a standards body called the IETF, Internet Engineering Task Force, that writes documents. In fact, anybody can write documents, and then the standard body will accept or reject them, or discuss them, certainly. Some of those RFCs are called Internet standards. The collection of all these standards is the architecture. That's all the rules that we apply to make this very, very complex and huge, monstrous system called the Internet work. Right? We need rule to avoid chaos. Right? One of the rules says an IP public address is used in the public Internet. A private address can be used only in private domains. But most of us at home, if we look at the IP address that we have on my PC when I am at home behind my ADSL modem, I will find an address like this one. Or this one. Right? So this is my configuration at home. I have a few machines that are interconnected by an Ethernet concentrator or a switch of some kind. They're also connected to the internet, and I have private addresses. So it should not work. I should not be able to go on the internet, but I can, of course. Otherwise, it's... So what do we do? Well, we use a box called Network Address Translation, NAT. And the main goal is to be able to use private addresses on the internet. Incidentally, by using private addresses, we reuse the public address that we still have. In fact, at home, I still have a public IPv4 address. It is the address that Swisscom, if I'm a customer of Swisscom, gives to my ADSL modem. So I still have a public public address, but usually I don't see it because few people look at their modem, although I encourage you to do by going, your modem has probably a web server. It's probably called 192.168.0.1 or .1.1, depending on the flavor. So if you go there, you will be able to see everything inside. And you will see that it has an IPv4 address. But usually, if you go to Swisscom and you say, oh, I have 5 PCs, 3 smartphones, 5 tablets, give me 32 IP addresses. You might, but the bill will be very expensive. You'll pay probably a few thousand francs a month for that, right? So no, I'll live with one address, and I'll put a device called a NAT that will be able not only to use the private address, but to reuse the same public address several times, which is another violation, obvious violation of the architecture that says one interface, one address. So how does it work? Well, it's a hack, although now it has become an official way of doing it. The idea is that the NAT, so this box here, looks not only at IP addresses, which is the normal job of a router, but it also looks a bit further into the headers of the thing that is inside IP. What is typically inside IP is TCP or UDP. There's also ICMP, but let's forget for a second. So it will typically, most of the things we do at home is TCP, and a few things are UDP. So what a NAT will do, it will look inside the packets for addresses, but also for one element of the UDP or TCP header, that's called the port number. We'll discuss that a bit later in 2 weeks. The port number is a number that is used by UDP or TCP to identify several flows. For example, if you're talking to a machine that has both a web browser and a DNS server, normally it doesn't happen, but the DNS server probably still has a little web server for managing it, for example. So if you speak to that machine, you need to know which program in the machine you're speaking to. This is made by using ports. So the idea is to look at the ports, and I'm illustrating, and remember, and keep remember in what is called a NAT table. So this NAT, for example, that serves 2 machines, 10.11 and 10.10, has only one IP address on the internet, and through some mechanism it has learned that all the traffic that comes from the machine 11 with a UDP port 1029 goes to the internet through a given destination that has another port number. Let's talk in a minute how this table is made. But let's see what happens to the packet. Assume this NAT receives a packet to this machine. It is to B. It's a UDP packet. Perhaps it's a DNS reply. B has done a DNS query to a DNS server, and this is the reply. So the reply is going to B. But of course, in the IP header, you don't see the IP address of B because it's a private address. What you will see is the IP address of the NAT, sometimes called the WAN side of things, so the WAN, wide area network, the WAN address of this installation. This one. Then it will have a UDP port number, 3441. Then what the NAT will do, it will receive this. Now the NAT doesn't know to whom it is, because the destination address is itself. Normally, a well-behaved machine, when it receives an IP address to itself, it consumes the IP packet, right? But here the consumption will cause a forwarding. So it's a special case of forwarding. It will go to the table and do an exact match, as opposed to longest prefix match. It will look in the NAC table for an exact match. Now the destination address comes from the internet side of things, the one side of things. So I go to the internet column and I look here, I have only 2 entries. I look whether one of the 2 matches exactly what I see in the packet. And what I see in the packet is the IP destination plus the port number. Now there is a match. The port number 3441 corresponds to this line, which is now a different IP address. So this NAT box will transform the IP destination address, which we have seen a router never does, but a NAT does. A NAT is not a router, even though in practice people will call it a router. It's not a router. It's a special box that is called a network address translation box. So the NAT will translate the packet, create another packet that will go to the correct local private address. Now, on the private side of the NAT, we are in the private network, so those private addresses will work. And it has also changed the UDP port number. Question?
Is there another protocol called PART to change the port address?
Say that again?
Because the LAT is to change the IP address, but is there another protocol called PART to change the port address?
So is there a protocol to
Called PART.
called PART?
Yeah, PART.
Perhaps you'll give me more information. I don't know this.
Okay.
Here it doesn't use any protocol. It is done by the NAT transparently. Right? So the machine B and the DNS server, let's say at the other end of the internet, none of them knows that there is a NAT. In fact, the DNS server thinks he is speaking to a machine that has this public address. He thinks he's speaking to the NAT. And he thinks in the NAT there are 2 processes with different port numbers that are speaking to itself. But each of those processes, in fact, are different machines. Right. Yes?
So, is it possible that you, in the LAN there is the same port and the same IP? Is this no?
Yes. So on purpose here, I use the same port number, which is very rare, but it can happen. So this port number, which is used by machine A and machine B, if they're exactly the same machine and they boot and do exactly the same job, perhaps they will use the same port number, even though there's so much randomness in machines. But it's possible that the same port number is used here in both. So this is, for example, your DNS resolver that is sending a query to a DNS server and uses this source port number here. And they are the same.
And there will be no conflict if someone sends a message and they receive it in that port.
There will be no there would be a conflict if we would put the same number here, but as you have seen, they are different.
No, in my computer.
In the 2 this is computer B, this is computer. There is a bug here. One of them must be 0. Yeah. One of them must be 0. Right? Of course, if they are twice the same, it's a little boring. It's not. So one of them must be 0 here. So, in summary, how does network address translation work? Well, it's a cute hack that consists in using the port numbers for addressing. The port numbers belong to the transport layer, but we use them for identifying machines. So we use them as network addresses. And of course, we need to build and maintain this table. So here I'm showing the other case of another request coming to that other machine. And now if the lines are correctly written, which should be the other way around, right? There should be 11 here and 0 here. Then the correct demultiplexing will take care. If the NAT did its job well, which consists in choosing different port numbers here, even though they were there. So what does a NAT do? On the receiving side, it does exact matching, but it does also swapping of addresses. It changes the IP addresses and the port numbers. Yes?
How does the internet know that the UDP is 3441?
How does the internet know that UDP is?
3441.
No, it doesn't know that UDP is 3441. So in this packet, there is an IP header with this destination address and a protocol type in the IP header that says it's UDP. And then there's a UDP header. Inside the UDP is a standard. We know where in the UDP header is the port number. So the NAT knows where to read the port number. Just like your pretty print, when you do Wireshark, prints the port numbers. So the NAT does the same thing. I will steal 2 minutes of your time to conclude with the last slide. How is the NAT table built? Well, the answer is it's done on the fly. You probably have never configured your NAT, though you can. You can log into your NAT and write those mappings manually. But it's painful and nobody likes to do it. So in principle, what the NAT does is learn. And it's based on the assumption that all the servers are in the internet and all the clients are on the local area side. So when you connect to a server, you send a packet. For example, B is going to a web server here. So it will send from its address. Now, when the first time B speaks to the web server, the NAT sees it's a new entry. I've never seen that combination of destination address and source address and source port number. I've never seen that. So it's a new thing. So what it will do is will create a new table where it will remember the TCP port number. Then it will pick a new port number that's available, one that was not already allocated. In this case, 2343. It's a TCP port, not a UDP port. And will change and pick this value. When the reply from the web server will come, then the web server will think it is the NAT that is speaking to it with this source port number. So it will reply to the NAT, but the NAT, of course, will not analyze the messages sent by the web server. It will go directly to the table, swap the TCP port number and the IP address back to their original values, and everything will work. Now, will it always work? Well, it works only if the communication always starts from the LAN. If you have a server at home, which you may have, right, your media server, and then it won't work, right? Because if somebody comes from the outside, gets into your NAT, the NAT doesn't handle the internet side in the way we said. So if you need to do something, so you have exotic terminology, it's called punching a hole through the NAT, you need then to manually configure the table to say to the NAT how to do, which table entry to do. It's possible if it's asymmetric, if both are behind NATs, like if A calls B at home using Skype, and both are behind the NAT, then it won't work. Skype doesn't work in that case. It works, but it doesn't work by sending directly from A to B. It will need an intermediate box in the middle to connect to, and then the two will connect to the intermediate boxes. So it needs some intermediate box in the internet. This is what made the fortune of Skype. Before Skype, you had to punch holes in your NATs to do IP telephony. So only a few people were able to do it. Otherwise, you need a third party to do it. So NATs are a hack. Like all hack, they have side effects. Here are some of the side effects that we see.